Hi everyone, my name is Dr. Sunny. So today I want to talk about water retention in soil. Okay, this diagram shows the available water for plant growth. So imagine a soil that after rainfall, so the soil will be filled up with water as shown here. So the soil is fully filled up by water. But when the soil is fully filled with water, and the water that fill up the soil also is easily flowing through the soil, and those water that easily flowing through the soil, that is what we call the gravitational water, so drain out of the root zone. Okay, so when the water that easily flow out from the soil is drained from the soil, at that stage it is called field capacity. All right, so at field capacity, uh, there are some holes between the soil particles, as you can see here. So this is the stage where it is called capillary water. So the water that left after gravitational water drain out, the water that left in the soil is called capillary water. So water held in micropores. So available water, plant root can absorb this. So this water, which is called capillary water, is also the water that available for plant root to extract. So if the water continue to dry as a result of plant root extractions, or even by evaporation or evapotranspirations, and then the water will dry to a stage where we call it as a wilting point. So at the wilting point, the water that left in the soil is called hygroscopic water. So the remaining water adheres to soil particles and is unavailable to plant. So this water cannot be extracted by plant because it is too strongly attached to the soil. So the best way for us to understand what kind of water that extracted to the soil at this stage is best described by, for example, if you take the soil that's wet, you put into an oven at 105 degrees Celsius for it to fully dry, and after 24 hours you take out the soil and you place it on top of the digital weighing machine. Then you can see over time the mass of the soil will increase up to a stage before it stops. So the increase of mass on the soil in the soil is due to the absorptions of water from the air. So the water from the air absorbed into the soil, they attach it to the soil. That water is called hygroscopic water, and that water is just a very small amount, and they are very strong attracted to the soil surface. All right. So this amount of water available in the soil at different amount at different stages of drying or evaporation. So it can be related to, the amount of water available in the soil can be related to the pressure in the soil. The pressure I'm talking about is not the positive pressure. The pressure that I'm talking about is the negative pressure. The negative pressure that I'm talking about is actually the metric suction, the suction of the soil, or the attraction forces of the soil towards the water. So the water is being pulled by the soil, and as a result of that, it results in a negative pressure. So we can relate the amount of water to the metric suction. Okay, so now let us look at the soil water content. Okay, water quantity in soil is expressed in two different units. Okay, the volumetric water content and the gravimetric water content. So the volumetric water content is equals to the volume of liquid water, which is VL, per volume of soil, which is VT. VT is the total volume of the soil. So Vt is actually represented by V soil particles, V air content, and V water content. Okay, and the gravimetric water content is given by mass of water ml per mass of dry soil ms, and they are related by the relation which is the density of water rho L multiplied by the volumetric water content theta L equals to the bulk density rho B multiplied by the gravimetric water content theta G. So you can see that the density of water, which is m liquid, mass of liquid, over volume of liquid, and the theta L, which is the volumetric water content, is given by VL, volume of liquid, over volume of soil, then equals to the bulk density, which is given by mass of soil divided by the volume of soil, and then of course multiply with the gravimetric water content, which has the mass of liquid over the mass of soil, a mass of dry soil. So this slide shows the fluid properties of water. So it's good to know a little bit the properties of water, and there are few different properties of water. For example, table 2.1 here shows some physical properties of pure water. For example, the density in the liquid form. Okay, you can have around 9.98 multiplied by 10 to the power 2 in a kilogram over meter cube at 20 degrees Celsius, right? But in a solid state you get a different density, and also in the vapor stage you have a different density, and of course at vapor stage you get a lower vapor density, right? There is also heat of fusions. Basically, heat of fusion is referring to the change of phase from a solid phase to liquid phase. So let's say in 1 kilogram of solid that converted from solid to liquid, it requires about 3.34 multiplied by 10 to the power 4 of joule in order for that to happen at 0 degree Celsius. Heat of vaporization, which involves the transformation from liquid phase to gas phase. So in 1 kilogram of liquid, the transformation from liquid to gas require about 2.45 multiplied by 10 to the power 5 of joule energy that is required at 20 degree Celsius. Specific heat is referring to the amount of energy that require to increase a unit of temperature, which is here referring to degrees Celsius. For 1 kilograms of liquid, okay, at 20 degrees Celsius, the amount of joule that required is 1 multiplied by 10 to the power -3, right? And dielectric constant is referring to the amount of charge that can be stored by the substance. Okay, in this case it's referring to the liquid water at 20 degrees Celsius. So it is 8 multiplied by 10 to the power 2. So the higher the dielectric constant means the better the substance that able to store charges. And for thermal conductivity is referring to how easy the substance that can allow the heat to flow through the substance. So in this case, the substance that we're referring to is the pure water. All right. So this case is for 20 degrees Celsius. All right. So we have around 6.03 multiplied by 10 to the power -2 joule per meter per second per degree Celsius. Okay. And viscosity is measuring the easiness of flow. So if the substance that has a high viscosity, basically means that that substance has a high restrictions to flow. If things that have a low viscosity, basically means that it is easy to flow. So in this case, for water at 20 degrees Celsius, it is 1 multiplied with 10 to the power negative 3 kilogram per meter per second, right? Surface tension is referring to the ability of the substance to pull itself together to form a smaller surface. For example, if you take a drop of liquid, you drop in the air, and the liquid will pull itself together to form a sphere. And this is the result of attraction forces between the water molecule. So the water molecule try to form the smallest volume possible that they can have the smallest surface area. So the surface tension is to pull itself together. The surface tension is measuring the ability of the substance to pull itself together. So in this case, it is 7.27 multiplied with 10 to the power negative 2 joule over meter square. That's why you can see that they are referring to the surface area. So the amount of energy required per meter square. Okay. So this diagram shows two figures, figure A and figure B. Figure A has a horizontal surface area of water, and figure B has a cave-in surface area. The only difference between these two diagrams is that the horizontal surface is showing that the water at the surface is attracted into the bulk of water, but it's not that strong when compared to the attraction forces in figure B. The figure B, you can see that the curvature, the surface of the water is caved in towards the water body. Basically, it means that the attractions forces by the water molecule at the surface of water in diagram B is much stronger than the attraction shown in diagram A. So it means that the attraction here, pulling forces in diagram B, the water molecule in diagram B is much more stronger, right? As a result, it caused the cave-in to take place. So here shows the equations for a hemisphere interface of curvature R between pure water and air. The pressure difference, changes of pressure between the air and liquid sides of the interface is given by the change of pressure equals to 2 multiplied by surface tension divided by R. So the derivation is shown here. So let's say you have a hemisphere. So this side is filled with water, and then the other side is filled with air. So you have a pressure from air pushing in the liquid surface, and then the pressure coming from the liquid that's opposite the pressure from air, and then you have a surface tension on the side of the hemisphere interface, where this surface tension is given by this symbol. All right, so and this surface tension is acting on the line of the hemispherical surface. So you have the line that is 2 pi r, okay, and then the pressure is acting on the surface area. The surface area is pi r square. All right, so we have a pressure difference, pressure of air minus by pressure of liquid in bracket multiplied by the surface area of the hemispherical, and then equals to the surface tension multiplied by the line of the hemispherical. So you get 2 pi r. So in the end, you can arrange and you get the pressure of the change of pressure equals to 2 multiplied by surface tension divided by r. So this is exactly the equation you have here. All right, I forget to mention also the hemispherical has a radius of r. The figure 2.3 shows the relationship between interfacial curvature and pressure difference between the liquid shaded and gas unshaded phases. So the air-water interface is shown as a solid line. So in the case here, the first case here, you can see that the pressure from the liquid is actually greater than the pressure of gas. As a result, the air-water interface cave out from the liquid surface. And the figure number 2 here shows that the pressure of gas equal to the pressure of liquid. So in this case, there's no curvature, no cave in or no cave out actually happening. So the water level is actually horizontal. And for the last diagram, it shows the pressure of gas is actually greater than the pressure of liquid. In this case, the greater pressure of gas pushing in the liquid surface. As a result, we can see a cave in of the liquid, the air-water interface. So there is a cave in of air-water interface due to higher pressure from the gas than the pressure from the liquid. This diagram shows a method that is used to measure a property of water. Alright, so imagine a plate that is massless, almost massless, that is placed on top of a liquid volume, and then the liquid volume is quite thin, and then that we have a stationary plate at the bottom that's not moving. But stationary it means that the plate is not moving. All right, and then we pull the plate with a force F, and resulting a plate to move at the velocity V max. As a result of that, the water molecule that attached to the surface of the plate will be moving at the maximum velocity. The maximum velocity will be V max, right? And the water molecule that attached to the stationary plate will be stationary. So the water molecule that attached to the stationary plate is not moving, where the water molecule that attached to the upper plate, the moving plate, is moving at the speed of the plate. So as a result of that, we can create a velocity gradient where we have a change of we have a different velocity with different depths. So the velocity increases linearly with the depth with the height of the liquid. Okay, so with that we can cause the formations of a velocity gradient. So at a different height, which is the y, so you have a different velocity. So dv over dy, okay, will be proportional to the force that apply on the upper plate, and the area of the plate is A. So we have a force over A, which is called the shear stress. All right, and the velocity gradient, which is the shear rate. So shear stress is directly proportional to the shear rate, and they are equal when this relation is multiplied by a coefficient. The coefficient here is called the dynamic viscosity. Okay, so this whole relationship is called the Newton's law of viscosity. So the dynamic viscosity is measuring the viscosity of the liquid located between the stationary plate and the moving plate. All right. Direct measurement of soil water content. So to obtain gravimetric water content, we can use the convective oven dry method. Okay, a soil sample is measured by weighing it. So a soil that is wet, we measure the mass. The mass will give us the mass of liquid plus the mass of solid. Okay, so drying it to remove the water at 105 degrees Celsius for 24 hours in a convective oven. Convective oven is basically means the oven that allow the air to go through circulation with the external air, right? And then reweighting it again means measure the mass again after it is dry, and the mass that we get is actually the ms, so only the mass of solid, right? So the gravimetric water content theta g is given by theta g equals to ml plus s minus ms divided by ms. Okay, so if we know the bulk density of the soil and also the liquid density, then we can actually estimate the volumetric water content. Right, the slide here shows the example 2.6, which calculate the gravimetric water content. Okay, so a can of moist soil is brought to the lab and weighed, dry and reweighed. The following data are taken. So mass of can with moist soil is 140 gram, mass of can with dry soil is 120 gram, and mass of empty can is 20 gram. Right, so to find the theta g, the gravimetric water content, first we must know the mass of water. So the mass of water can actually be found by taking the 140 gram minus the 120 gram. So because the dry soil is only the soil, and the moist soil, it contains the water and the soil. Okay, so the 140 minus 120, we know the mass of the water, right? And then we need to divide by the mass of dry soil. So the mass of dry soil can be determined by taking 120 grams of dry soil with the can minus the mass of the empty can. Okay, so 120 minus 20, so you get around 100, and then 140 minus 120, you get around 20. So 20 divided by 100, 20 divided by 100, you get 0.2 kilogram over kilogram, or you can also written as gram over gram. Okay, so we're also interested to know the volumetric water content apart from the gravimetric water content. So the volumetric water content theta L can be estimated from theta G, which is the gravimetric water content, if the bulk density rho B is known. So we also need to know the water density rho L, which depends on temperature. In normal room temperature, it can be assumed to 1000 kilogram per meter cube. So the density of water can be assumed as 1000 kilogram per meter cube at normal room temperature. So knowing that rho L multiplied by theta L equals to rho B multiplied by theta G, hence theta L, the volumetric water content, it is equals to bulk density multiplied by the gravimetric water content divided by the density of water, which is 1000 kilogram per meter cube. Okay, so that is a indirect measurements of volumetric water content theta L by electromagnetic radiation method. Indirect measurement basically means we are not measuring it directly. So just now we talked about taking the can or the soil sampler, we hammer it down into the soil, we take the soil sample, we'll go back to the lab, we dry it in the oven, and then we know the mass of water, and then we divide with the mass of the soil, and then we can get the gravimetric water content. So if we know the density of water, we know the bulk density of the soil, then we can actually estimate the volumetric water content, and that is the direct method. But using indirect method basically means you are measuring it in an indirect way. So this method that they use to measure the water content in an indirect way is called the electromagnetic radiation method. The volume of soil will have a water content dependent transmission of radiation. So basically there are three methods listed here. So the volumetric water content measurement by time domain refractometry. There is also volumetric water content measurement by neutron attenuation, and also measurement by gamma ray attenuation. Here we only discuss about the measurement by time domain refractometry. So this diagram shows the time domain refractometry measurement method. So you have a probe with 3 legs. So this is the leg where you push into the soil to measure the soil moisture content. Okay, so here is the volumetric water content measurement by time domain refractometry, or TDR. Okay, TDR is to estimate volumetric water content indirectly by measuring the permittivity, okay, given by this symbol, which relates to dielectric constant of the soil. then calibrate the relationship between volumetric water content and the permittivity. So these sensors will measure the permittivity, and as the volumetric water content in the soil is changing, the permittivity will also change with the volumetric water content. So permittivity is measured by placing a prong with two arms. This is a prong with two arms, okay, forming two parallel waveguides, okay, two parallel waveguides into the soil. So this sensor will be pressed into the soil. Only okay, this waveguide, okay, and sending a step pulse of electromagnetic radiation along the guide. So a step pulse will be sent from the meter through the wire to the prong and to the waveguide, and then the signal will be sent back, okay, to the prong, to the wire, and to the meter, okay. And the pulse reflected, so the pulse that reach here and then go back, reach here and then go back to the source. So the pulse reflected at the end of the prong and return to the source, where it travels. Time and velocity can be estimated with an oscilloscope. So the meter here not only measuring but also has an oscilloscope that able to read the returning pulse, okay. The permittivity of soil between waveguide causes the velocity of the pulse to deviate in a known manner, okay, from the velocity of light in vacuum. So let's say here you put it in a vacuum, you will get a different returning time and velocity, okay. So if you put it in the soil, you will get a different returning time and velocity. If you put it in a soil that has different water content, you also will get a different time and velocity. So with that, we can actually do a simple correlation between the volumetric water content with the permittivity. So this is basically the polynomial equation that used to relate the permittivity with the volumetric water content. All right. So hence the permittivity can be estimated from the travel time, and the volumetric water content can be calculated by a regression equation from the permittivity. So here is to establish the relationship between the volumetric water content and the permittivity. So this is the equation. All right. Components of the soil water potential. So there is gravitational potential, okay, solute potential, tensiometer pressure potential, metric potential, air pressure potential, and hydrostatic pressure potential. Gravitational potential. Gravitational potential is the energy per unit volume, so it's a joule per meter cube, which is also equals to Newton over meter square, or equals to pressure, okay, of water required to move an infinitesimal amount of pure free water from the reference elevation Z0 to the soil water elevation Z soil. So gravitational potential is equals to rho L multiplied by gravity in bracket Z soil minus Z0. So the rho L is the water density and G is the gravity. So the easiest way to understand how the gravitational potential works is that initially, let's say the water is at the lower elevation, Z0, and then you take it up to a higher elevation, Z soil. As a result of raising the height from lower elevation to a higher elevation, and this resulted in the increase of gravitational potential. Similarly, if it's at a higher elevation and you take it down to a lower elevation, you reduces the gravitational potential. Solute potential. The solute or osmotic potential is the change in energy per unit volume of water when Solutes identical in composition to the soil solution at the point of interest in the soil are added to pure free water at the elevation of the soil. So this can be viewed as when the water is when the water in the soil is free from any solute, and then now you take the solute, you place it into the soil at the elevation that they're talking about, then you change the potential of the water, and the potential that you change in the water is what you call as a solute potential or osmotic potential. Tensiometer pressure potential. The tensiometer pressure potential is the energy per unit volume required to transfer reversible and isothermally an infinitesimal amount of solution containing solute which are identical in composition to the soil water from the reservoir of solution which is at reference pressure and is located at the elevation of the soil to the point of interest in the soil. The effects include all forces on soil water except gravity and solute. Its influence may include the effects of binding to the soil solids, interfacial curvature, air pressure, weight of overlying soil solid material, and hydrostatic water pressure in saturated soil. So the easiest way to understand this is that it is basically the relocation of water, okay, relocation of water that may contain solute but does not include the effects of solute. So if the water that contains solute at a location x1, now we try to relocate it to a location x2 which is also horizontal, right? Therefore these effects potentiometer pressure potential effects are created, right? So we basically relocate the water that contains the solute from a location to another location, okay, that is in a horizontal direction, right? And this is how we created the tensiometer pressure potential. So it does not include the effects of solute because the relocation location also has the same amount of solute. So the osmotic potential can be excluded from this pressure from this potential, and also the gravitational effects can be excluded because we relocate it horizontally. So only vertical relocation can cause the gravitational potential. Okay. Metric potential. The metric potential is the energy per unit volume of water required to transfer an infinitesimal quantity of water from a reference pool of soil water at the elevation of the soil to the point of interest in the soil at reference air pressure. So metric potential is basically the relocation of the water from point x1 to a point x2. So x1 and x2 is in the horizontal plane. So when we relocate the point from point 1 to point 2, we cause the metric potential to happen. Okay. So here is a diagram to show you. This is a figure to show you the importance of metric potential. For example, when the water is fully saturated in the soil, so the metric suction or the metric potential is 0. Okay. So when the water start draining from the soil to reach the field capacity, the pressure is about 0.033 megapascal. At that point, you reach the field capacity. So that this pressure 0.033 megapascal is actually the metric suction or the metric potential, and you can see there's a negative value. The negative value indicates that this is a suction or the negative pressure. Okay, and then when the pressure continue to drop up to a stage where we reach the permanent wilting point, or that is the reason why they call it permanent wilting point. Permanent wilting point basically it means that at this stage the leaf of the plant will start to wilt. Means in Bahasa Malaysia we will say that the at this pressure the down kulit down pokok down tumbuhan bermula menjadi layu. That's what they mean, melting point. Okay, so the pressure is 1.5 megapascal, or in kilopascal we call it 1500 kilopascal. Okay, so here is 1.5 megapascal. You can see that it's a negative, so it's the suction becomes so strong that it pull the soil, pull the water very strong, up to a stage where the root of the plant try to compete with the soil. The root lose, because the root the roots, the plant roots extractions of water from the soil is not as strong as the extraction of the soil towards the water. So in this case, the roots of the plant fail to extract water because the extraction, the suction pressure by the soil is very strong at this point. So this point is called permanent wetting point, and the pressure is negative 1.5 megapascal. Air pressure potential. The air pressure potential is defined as a change in potential energy per unit volume of water when the soil air pressure is changed from the pressure of the reference state to the pressure of the soil. So air pressure potential can be approximated by the air pressure in the soil minus with the air pressure of the reference. So here you can get the change of pressure due to air pressure changes. Hydrostatic pressure potential. The hydrostatic pressure potential is defined as the water pressure exerted by overlying unsupported saturated water on the point of interest in the soil. For example, you can have the ZWT as a reference point, and then at Z soil, at the deeper part of the soil. So when you want to calculate the pressure at Z soil, so we can take this hydrostatic pressure potential equals to the rho L, which is the density of water, multiplied by the gravity, which is about 10, and then multiplied in the bracket, which shows the depth of the soil, minus the reference point, the ZWT. So the Z soil here is greater than 0, and the ZWT, we can take it as a 0. Okay, so you will have the pressure at the point of Z soil. Okay, for swelling soil. So soil can expand in size, which is due to clay. So as you know, the textural, the soil's textural component, there are three: sand, silt, and clay. So when this component come in contact with water, only clay can increase in volume. The clay increase in volume, that's what we call swelling soil. So for swelling soil, additional two potentials to consider. The first potential to consider is the overburden pressure potential, and the second potential to consider is the wetness potential. The wetness potential basically means kebole basahan. This is what it means, wetness potential. So overburden pressure potential is when the soil is sufficiently saturated that there is no contact between the solid particle and there is no external load on the system. The envelope pressure is equal to the pressure due to the weight of the overlying soil. So the overburden pressure potential can be best explained in this way. So imagine you have a clay particle at the bottom and a clay particle at the top. Okay, initially they are in contact with one another, but after the clay soil absorb the water, the clay particles start to detach from one another. So when they detach from one another, basically means the space between them is actually filled up with water. So imagine that the particle at the bottom, the clay particle at the bottom, has to handle the pressure of water on the top, and also the pressure of the particle coming from the top. So that is what we call the overburden pressure, or in this example they call it envelope pressure. Okay. Alright, now we'll talk about the analysis of system at equilibrium. So two systems at the same temperature containing water at different energy state come into contact. Water will flow from the region of higher total potential to the region of lower total potential. Flow continue until the two system total potential energy is the same. Flow stop, equilibrium is achieved. All points of water system at equilibrium have the same value of total water potential energy. Okay, so here is the table. Table 2.3 shows the components of total soil water potential for various applications. And the symbol is listed here. So we have a gravitational potential, solute potential, tensiometer pressure potential, metric potential, air pressure potential, hydrostatic pressure potential, overburden pressure potential, and wetness potential. So if you look at this, you can see that the application can be broadly divided into unsaturated, means for soil that is partially filled with water, or in Bahasa Malaysia we call it tanah separa tepu dengan air. And then we have a saturated soil. Saturated soil basically means referring to groundwater, or the soil that is fully saturated with water, or in Bahasa Malaysia maksudnya itu tanah yang penuh dengan air. So ini tanah yang tidak penuh dengan air tapi mempunyai sedikit air. Ini pula tanah yang penuh dengan air. Okay, so you can see the broad difference between them is that we still have this gravitational potential for all of them. We also have solid potential for all of them. So if the water in the soil does not have solute, so this solid potential or osmotic potential can be neglected. So if the soil has solute, then this solid potential has to be taken into account. And so if for unsaturated soil, we have this metric suction, okay, metric potential. So Wm. So okay, metric potential. So we have metric potential for unsaturated soil, whether it's a swelling or rigid. Swelling basically means that it can be the soil can be expanded in size, or rigid basically means that the size is remaining the same whether it's wet or dry. So that's what you mean by rigid and swelling. So you can see that unsaturated soil, we consider this metric potential, or metric for both of them, or this is also called the metric suction potential. Okay, and then we have this also the air pressure. Okay, the air pressure potential, all right. But if you look at saturated soil, the difference is that they doesn't have this Wm, they doesn't have metric potential. Okay, so they only have this pressure, is what you call that, this hydrostatic pressure. Okay, hydrostatic pressure for swelling and also for rigid soil. For saturated swelling soil, we have hydrostatic pressure potential. For saturated rigid soil, we have hydrostatic pressure potential. But when it comes to this unsaturated soil, we have metric suction, and also this what you call that, air pressure potential. So the air pressure potential is referring to the pressure pressure of air in the soil. So here this Wp, the hydrostatic pressure potential, is referring to the pressure of water in the soil. Okay, so that's the difference. This is referring to the air, this is referring to the pressure in the water. Okay, okay, so that is also a similarity. All of them can also consider this tensiometer pressure potential. Okay, all of them can consider it. And also the one of the unique thing about the unsaturated soil is that it can consider the wetness potential. So this one is specifically available for clay, and also for this we call it overburden pressure potential, only for swelling clay. Okay, for swelling clay. All right, then but you also see that in a saturated soil you have this overburden pressure potential. Okay, that's also possible for saturated swelling soil. All right, so but mostly in most of the cases, when we deal with unsaturated soil, we will have this air pressure potential and also this metric potential. But when we deal with saturated soil, we will deal with the hydrostatic pressure and also this overburden pressure potential. But sometimes we don't have that, and we only deal with the hydrostatic pressure potential. Okay, and so you might also want to ask why is it necessary to know the total soil water potential? Because in the soil, we are normally interested to compare 2 points, point A and point B. So in order to compare the point, we have to know the energy level at the point before we can compare it to the energy level at a different point. So you can see that we have a total potential for each different category of soil condition. So we can compare the total potential of point 1 with the total water potential at point B. Okay. Okay, now let's look at table 2.4, analysis of components of the soil water potential at the point of interest using the equilibrium principle. So step 1, verify that the system is at equilibrium. Equilibrium basically means the system itu adalah stabil. Okay, so water flow must be zero, so means tiada pengaliran air, okay, or negligible everywhere, and the temperature must be constant. So suhu di dalam sistem itu mesti constant, tidak berubah. Okay, and step 2, define a reference elevation. Mesti ada kedudukan ketinggian dia pada tempat di mana kita pilih dia sebagai point of reference, tempat di mana kita pilih sebagai rujukan. And the reference air pressure, so apakah tekanan udara rujukan. So we must define the reference elevation and the reference of air pressure. That is step 2. Step 3, find a location in the system where the total water potential WT may be estimated, and call this value WT naught. Okay, and step 4, set WT equals to WT naught at the point of interest. Okay, so kita pilih satu kawasan di mana kita boleh di mana kita boleh tentukan total water potential pada titik itu, dan kita setkan titik itu sebagai WT naught. And WT naught ni mesti pada kedudukan yang kita berminat. Okay, point of interest yang kita nak tentukan. Okay, total potential itu. And step 5, divide the WT into appropriate component using table 2.3. Table 2.3 yang slide lepas tu, ya kan, table 2.3 ni. Okay, so kita gunakan table 2.3 ni, yang persamaan ini, yang kita kena pilih salah satu lah yang sesuai untuk sistem kita. So we must pick an equation that is appropriate lah, based on table 2.3. So we pick the component of this equation that is appropriate to our system. Okay, and step 6, evaluate directly those components for which appropriate information at the point of interest is available. So we look at this equation, the component. There are so many components. We have to determine one by one of these components. Let's say we choose unsaturated swelling soil, and let's say we choose equation number 2. So WT equals to the gravitational potential plus the solute potential plus the air pressure potential and plus the metric potential. Okay, so we must be able to determine one by one of these potential. Okay, that's step 6. Okay. Okay, step 7, determine the remaining component or sum of components using the equation in step 4. Okay, so we have to determine one by one of those potential at the point of interest. And after that is done, we can find that, compare that with another point of interest. So we might need to compare 2 points. So the first point, we must determine all the potential for each component, and for point 2, we must also determine the what you call that, the potential for each component at point 2. Okay. Okay, now let us look at example 2.9. Example 2.9, calculate the height of rise of water in a clean glass cylindrical capillary tube of radius r placed in an open vessel of pure water. Assume that the contact angle of the water on glass is 0 and that the air above the interface is at the same pressure as the air above the open vessel. So here is a let me see. Okay, so here is a open vessel, and here is the air above the interface. Okay, so in this question we assume that the evaporation of water in the air has been suppressed or is negligible. So we want to find the height. We want to find the height of rise of water in a clean glass cylindrical capillary tube of radius r. Okay, so how can we do that? First, we must have a reference point. Okay, the reference point here is A, and then the second reference point, the second point is B. So if we refer back to our lectures previously, we need to know the total potential, okay, for a reference point, okay, and then we can compare that total potential at the second point. Okay, so let us define our first point as A, okay, and our second point as B. Okay, so we try to have total potential for point A, right, and then we also need to find the total potential for point B, so we can compare. So at equilibrium, total potential point A must be equals to total potential at point B. Okay, now we try to find the total potential for point A. So the point A, we must know what is the potential we are going to take into account of. So the total potential, the component that we are going to take into account of is the metric, the gravitational potential at point A. We also take into account the solute potential at point A, or also the metric potential at point A. Okay, right. Okay, the reason we take into metric potential is called is that we have this glass cylindrical capillary tube. Though there's no soil here, but we have a cylindrical tube that behaves like a soil, because this tube is attracting the water up in the tube. That's why we have this metric potential here. Okay, so we try to find the component. What's the component value for this? So WZA, the gravitational potential for point A, you can take it as 0, okay, because we can take it as a reference, and then we can refer to solute. Solute is 0 also, because there's no solute, and point A is also 0 here. Okay, the metric potential is also 0. Now we try to find the total potential for point B. So the component is also the same, Z, B. Okay, potential, solute potential, point B. Okay, and the metric potential for point B as well. Okay, so now we can find gravitational potential point A is rho G H. Okay, the elevation H. Okay, and then solute, of course there's no solute here, and the metric suction here, yeah, we can place it as a WM B. So we can equal WTA, okay, total TA, and total potential at point B. Okay, so it's 0 equals to rho GH plus W metric potential, right? So the metric potential the metric potential is actually given by this relationship. Difference of pressure equals to 2 surface tension divided by R. Okay, so this is a surface tension equation. Though it's a positive, but actually the surface tension force is acting upward. Okay, upward, which is contradict to the directions that is pressure that is facing downward. As a result, we have to take this equation as a negative. So we have to write here negative 2 multiplied by surface tension divided by R. So in this case, the H, the capillary rise is equals to 2 multiplied by surface tension divided by rho G and R. So the G here is a liquid water density, and G here is a gravity, and R is the radius of the glass cylindrical capillary tube. Alright, now let's look at example 210. Okay, 210. So repeat example 2.9 for the case where the open vessel contains a solution of osmotic pressure pi, energy per volume, and the capillary has a perfect semi-permeable membrane at the bottom that restrict the passage of solute but allow water to flow into the capillary tube. Okay, assume that the surface tension and contact angles are unaffected by the additions of solute. So you see here, you have a solute at the bottom that create the solute potential of negative pi. Okay, negative pi. All right, I change to red so you can see clearly. All right, and then they have a membrane. Okay, that prevent the solute from going upward. Okay, and now our job is to find the potential at point A and then compare with the potential at point B. So we know that the water will rise at the elevation of H. So how is that different right now? And we know the radius of the cylindrical tube is R. Okay, right. So let us write out the equation. So we must know that the total potential at point A must be equals to the total potential at point B. So WTA must be equals to WTB. Okay, so WTA, okay, we account for the gravitational potential. Okay, gravitational potential. We also account for the solute potential. Okay, solute potential. We also account for the metric suction. Okay, metric suction. Alright, so we can write down the equation here is at point A, the gravitational potential, we pick it as a reference point, so it's 0. Okay, but for solute here, we have a negative pi. Okay, as given here as a negative pi, and then the metric suction here is 0 because nothing is pulling the water. Alright, okay, so it means that no soil is pulling the water and no capillary tube is pulling the water. Right, so total potential at point B, TB. Okay, so we should write the same potential component. Okay, same, and similarly here. All right. Okay, so the gravitational potential at point B. Okay, we know that is rho G H. Okay, it's increased. And then the solute potential here is 0 because there's no salt here. Okay, right, and the metric suction at point B here is we know that it's negative 2 multiplied by surface tension divided by R, because we already know that the surface tension is given by this equation. All right, 2 multiplied by surface tension divided by R, but the surface tension here is acting upward. Okay, acting upward. Let me more clearly here. It's acting upward. Okay, so the water here is pulling upward. Okay, so it's is against the pressure direction. The pressure direction of water is normally going downward. All right. Okay, so let us equate the total potential of point A with total potential of point B. So we get negative pi equals to rho GH minus 2 surface tension divided by R. So the H here is given by 2 surface tension R. You can write straight away rho GR minus pi OG. Okay, so here is the equation for estimating the height of water rise after including salt solution with a membrane that preventing the solute, the salt from going upward. Okay, there you have it. So here I present to you the direct measurement of potential component. For gravitational potential, we can measure the vertical distance from the reference elevation to the point of interest with a ruler, for example. For solute and or osmotic potential, we can extract soil solution and measure its osmotic pressure, or analyze for solute concentration. Standard methods such as equilibrium dialysis or vapor pressure depression can be used. For air pressure potential, measure soil air pressure with a barometer and subtract the reference air pressure. Okay. And for hydrostatic pressure potential, we can measure the vertical height of saturated water or water table location above the point of interest. Okay. There are 3 measurement devices we discuss here: the piezometer tube, the tensiometer, the soil psychrometer. Okay, now we talk about the piezometer tube. Okay, so we have figure A and figure B. The figure A is a column of soil, but the column of soil that is just a portion of it is saturated. Okay, and a portion of it is unsaturated. But this soil is rigid. Okay, this soil is non-swelling or rigid soil, and figure B is a swelling soil. So you can imagine that the swelling soil is some kind of clay. So also a portion will be saturated and a portion is not saturated. Alright, so let's look at the figure A, the rigid soil. So in rigid soil, the water in the piezometer will rise to the height equals to the water table height. So the water rise, the water height in the piezometer tube will be equal to the height of water table in the soil column. Okay, so in the figure B, which is a swelling soil, so the height will reach, the height in the piezometer tube will reach exceed the height of water table, okay, by an amount equal to the overburden potential head. So here is a water table, but when you look at the piezometer tube, the water height, the water level is higher than the water table in the soil column. This is because there is an overburden of soil as well as the water itself that above the saturated soil. Okay, so this is for swelling soil. Alright, let's look at tensiometer. Tensiometer consists of water saturated porous ceramic cup connected to a manometer that is water filled tube. Okay, so we have a ceramic cup and we have a manometer tube which is filled with water, and then at the end of it you have a vacuum gauge. Okay, and the ceramic cup is deep into the soil. So here is a soil surface. Okay, similarly we also have a surface soil here, and the ceramic cup is deep into the soil, and there's also a manometer tube here, and at the end of a manometer tube they are exposed to the mercury. So in the manometer tube they are filled with water. Similarly for this one also, for figure A and B, the manometer tube is filled with water, and at one end it come in contact with vacuum gauge, and for the figure B, it come in contact with the mercury liquid. Right. So the tensiometer consists of water saturated porous ceramic cup connected to a manometer that is water filled tube. Okay, ceramic cup is made of very fine pore. Okay, very fine pores, means that they are very small size of particles, remain water saturated when in contact with the soil at relatively low water potential. So means it is fully saturated, so there's almost no pressure in it. Upon contact, water moves from the tube to the soil. So it means the soil actually pulling the water out from the ceramic cup. So creating suction at the manometer end until equilibrium is reached. So when the water is pulled out from the ceramic cup, so the water in the manometer tube will be pulled as well. As a result, the vacuum gauge will indicate that the water is being pulled, or the mercury, as you can see, the mercury will be pulled out. When the water in the tube, in the manometer tube, is being pulled down by the soil, then the mercury liquid will be pulled out. Okay, as a result of water in the manometer tube being pulled out by the soil. Okay, that's how it works. So and the total potential of the water is equal everywhere in the system, consisting of the soil and the device. Okay. Okay, let's look at this manometer. Not manometer. This tensiometer. Okay. So we are trying to derive an equation for this tensiometer. Alright, so we have to pick a reference point. So our reference point, we have both point A and point B, and then we pick here the soil surface as zero pressure. Okay, as a zero pressure. So we want to derive an equation for this. So we must find the total energy, total potential for point A, and then we must equal it to the point B. Okay, so let us find out what is the potential component for point A. All right, so for point A, we can take into account this gravitational potential. We can also take into account the metric potential. Okay, and also include the what I call air pressure. This hydrostatic potential. Okay, hydrostatic potential. All right, so we try to list out the value for them. So gravitational at point A, we have H as well as X. Okay, so we have rho. Okay, rho G in bracket H plus X. Okay, so we have gravitational potential and metric potential. Metric potential in this case is because there's no soil, so metric potential is actually 0. All right, how about the hydrostatic potential? So hydrostatic potential here, I think we have to take into account that the mercury is being pulled out, so it has to be negative. Rho mercury G up as a X. Okay, and also the atmospheric pressure. Okay, atmospheric pressure, PATM. Okay, I think the best way to do this is let me see if I could change this a little bit. Okay, yeah, so it's supposed to be like this. So how about we take into account total potential for point B. Okay, similarly we list out the component. All right, so what do we get here? If you look at the gravitational potential, the point B is L below the soil surface, because soil surface is a reference pressure point, so we have to take negative rho g L, okay, negative because it's below, right? And that's how about the metric suction? Yeah, there is a metric potential. Okay, there is a metric potential. Okay, we don't know the metric potential, and then we want to find the hydrostatic pressure. The hydrostatic pressure here is P A T M. So now we are going to equate TA, okay, the metric potential total for point B. Alright, so what can we get from here? We can get rho G H X, okay, minus rho M G X plus P A T M. I think it's better that we remove the atmospheric pressure. In this case, it's better we remove it, not consider here, because it's the same for both of them. Okay, for both A and B. So we neglect the atmospheric pressure. Alright, so in this case the equation is a bit shorter. Alright, so we get rho GL plus W, the metric potential. Alright, so we rearrange the equation. Okay, and then if we can take the metric potential as rho G H, okay, then and this one is H equals to H plus L minus rho M rho divided by rho X, okay. Alright, because we place the metric suction potential with rho GH, so we put this here, and then we can cancel out the rho and the G, okay, for both sides, and we know that rho M is 13,600 kilogram per meter cube, and rho is 1000 kilogram over meter cube. Alright, so in this case the H is H plus L, okay, minus 12,600 over 1000, okay, X. So we can write it as H plus L minus 12.6 X, okay. So that's the equation we derive, okay, that can relate the rise of mercury X, okay, the height X rise in the mercury, and relate it to the suction of water head, caused by the soil, okay. So that is also an alternative method how we can go about this. So we start from here, okay, from here we can take it as a from the point where it begins. So we start with let me see, start with the atmospheric pressure. So we have this is method 1, okay. So the one I show you here is method 1, okay. So that is a method 2. Method 2, how we can actually derive the equation. Okay, using method 2, we know that atmospheric pressure. Okay, so the atmospheric pressure will actually act on the surface of the mercury. Okay, so we have atmospheric pressure, and the mercury rise. So it's rise, that is a negative rho G X. Okay, and then if we draw a horizontal line, okay, we can see that there is a pressure increase. Okay, initially the mercury go up. When it's go up, it is minus. Okay, it's minus rho gx. So when it's coming down, it's plus. Okay, it's positive. Okay, positive. So we have a height of x plus h. So it's rho. Okay, so sorry, I forget to write it down for mercury. Okay, so it's a rho mercury g x. Okay, and now it's coming down positive. Okay, coming down, it's rho for water, g gravity, and it's h plus x. Okay, plus x. All right. Okay, and also include the L distance until we meet the porous cap. So it's rho g L. Okay, plus, and then it will be equals to the metric suction potential. Right, and of course the metric suction potential also has to account for the atmospheric pressure. So in this case, atmospheric pressure can be cancelled out. Okay, can be cancelled out. Right, so you can simplify the equation further into this form: O G H plus X, okay, minus rho M G X plus rho G L. So we can take metric potential for point B as rho G H, and here is rho G H plus L minus rho M minus rho G X. Okay, so we can cancel out the rho G, so we have H plus L minus rho M minus rho divided by rho. Okay, that will be x. So we already know that the rho of mercury, the density of mercury minus the density of water divided by density of water is actually 12.6. So we can simply write it as H plus L minus 12.6 x. So we can see that we use different method, but can also derive getting the same formula. Okay, so here is another different diagram of tensiometer. So you might looks here like here like you have a different kind of equation, but actually it's the same types of equation. It's just that the variable that they use is slightly different. So in the end, you still get the same same estimation that you want to estimate the soil metric suction by using a tensiometer. So the tensiometer, you have a porous ceramic cup, and we have a manometer tube, and then you at the end of the manometer tube, either you have a what I call vacuum gauge to measure the pressure suction, or you can also use the mercury to represent the suction caused by the soil. Okay, now let us solve the example 2.11. So let us read the question. Calculate the metric potential measured by the tensiometer in the following application. A mercury manometer tensiometer, okay, so it's a tensiometer, all right, is placed so that the ceramic is 100 centimeter below mercury reservoir. So 100 centimeter below mercury reservoir. So in this case, it is H plus L equals to H plus L equals to 100 centimeter. Okay, all right, 100 centimeter below the mercury reservoir. So the mercury rise to a height of 20 centimeter. So the x is 20 centimeter. Right. So we can use the equation which is given as H plus L minus 12.6. Okay, from here. Okay, that's what we get. So H plus L is 100 centimeter, right, minus 12.6, 20 centimeter. So if we calculate, what do we get? We get about negative 152 centimeter. Okay, 152 centimeter. Alright, so the mercury rise above 20 centimeter. Okay, so calculate the metric potential of the soil. Metric potential. So we have the H. Okay, the H value. Okay, this is the H value. So the metric potential is Wm equals to rho GH. So the rho is 1000 kilogram per meter cube, which is the density of water. The G is about 9.81 meter over second square, okay, which is the gravity, and the H is negative 152. So we have to convert it into meter. So it's 10 to the power negative 2 meter, right? And the value we should get here is what do we get? Negative 149, negative 149, 11.2 Pascal, right? Pascal. So it can be converted as 14.9 kilo Pascal, right? So this is what we get for the metric potential. Okay, now let's look at soil psychrometer. Soil psychrometer measure the relative humidity (RH) of the water vapor in the soil, then the water potential (WW) of the vapor phase may be calculated. Okay, so when we know the relative humidity, okay, and we can use this equation to estimate the water potential. Right, so here's a conversion of this equation into a few different forms. So where the PV is actually the vapor pressure in Pascal, PV star is the saturated vapor pressure in Pascal, MW is the water molecular weight, okay, in kilogram per mole, and rho W is the water density, and R is a universal gas constant, and T is the temperature in Kelvin. Okay, so the WW is given by rho of water multiplied by G gravity and H the height of water. So in this case, the height is actually the soil metric suction and the G is gravity. At equilibrium, water vapor pressure is equals to the liquid water potential. Okay, so soil water potential measured by psychrometer is a sum of metrics and osmotic potential. Okay, so it influenced by water and solute in the soil. So the soil has water and also has solute. It will affect the soil water potential. Okay, so here is a diagram. Here's a figure shows the WP4, which is an instrument from meter group. Okay, so this WP4 is measuring water potential using vapor pressure, and the concept as we discussed in the previous slide. Okay, now let's look at the water characteristic function. Metric potential represents the effects of soil solid forces and interfacial curvature on water potential energy. The relationship between metric potential and the gravimetric or volumetric water content is called the water characteristic function or metric potential water content function. So it's a Wm dash theta L, or can be written as Wm in bracket theta L. So Wm is the metric potential, theta L is the water content. Okay, so this is done by measuring metric potential Wm and water content theta L simultaneously. Okay, so this is an instrument that is called hanging water column. It can be used to measure the metric suction from negative 10 kPa, 10 kilopascal to 0 kilopascal. So what we do here, what is done here is that initially there's two reservoirs. So one of the reservoir on top of it has a porous plate, and on top of the porous plate there is a soil sample, many soil samples located on top of it, and then the reservoir was initially at the same level, and then the one of the reservoir that's open to the atmospheric is then lower down, and after it is being lowered down, the system is left to achieve equilibrium. So when the reservoir is lower down, there will be a pool of water, and the water will be being pulled down. So as a result, we create the kind of suction. The suction will be based on the height from the middle of the soil sample to the height of the open reservoir. All right, so at the open reservoir, if the open reservoir is lower, the suction will be even greater because the H will be even greater. Okay, and then after some time, we can take out the soil sample to measure for the soil water content. So that's how we can relate the metric suction with the soil moisture content. So here's an explanation for the hanging water column. Okay, hanging water column. So water saturated highly permeable porous ceramic plate connected at the top of the water column. Okay, so the water reservoir height is even with the top of the plate. Okay, water saturated soil sample held in a ring placed in contact at the top of the water saturated porous ceramic plate, and then the water reservoir is lower to a new height, a distant H below the top of the plate. The water will flow from the soil to the reservoir until equilibrium is achieved. In equilibrium, the total water potential of the system is constant, where if you write Wm plus Wz, then Wm will be plus rho gh. So Wz will be equals to rho gh equals to 0. So Wn is therefore equals to negative rho gh. So we have negative here because it is a metric suction. Okay, it's a metric potential, which is metric suction of the soil. Okay, when equilibrium is achieved, remove some soil sample and measure the gravimetric or volumetric water content, and then continue to lower the reservoir, and a new set of sample will be measured. A good contact between soil and ceramic, equilibrium will be reached with, rapidly. That is, we have to wait for several hours for equilibrium to achieve before we can take out the soil sample to measure the soil water content. So the device range is limited by space available for lowering the water column. Okay. So here is a pressure plate. Pressure plate can measure between negative 10 kilopascal to negative 1,500 kilopascal. All right. So the pressure plate is that they have this porous plate, and then you have a soil sample on top of the pressure plate, and of course the soil sample is saturated with water. All right, so as the pressure increases, so the water in the soil sample will be pushed out. Okay, will be pressurized to flow out to the porous plate. Okay, so the porous plate and then drain the water out through the water filled tube. Okay, so this is how it how the soil moisture content are being measured at different pressure. So we know the metric suction potential and the soil water content, okay, at different pressurized environment. Okay, so here is a bit of explanation about the pressure plate. So the pressure plate consists of airtight chamber, okay, enclosing the porous ceramic plate connected to an underside tube that passes through the chamber to the open air. The saturated soil sample. So this is a saturated soil sample. The saturated soil sample in the ring placed on top and contact with the ceramic. Okay, so here is the ceramic. Okay, and the chamber is pressurized. Okay, so this is the chamber. The chamber is increasing the pressure, and the water flow from the soil pore through the ceramic and out of the tube. So the water here in the soil flow out through the ceramic and then through the tube. Okay. At equilibrium, water flow through the tube will cease. Means at equilibrium, no more water will flow out from this tube. Okay. So if you Wm plus Wa, so Wn is a metric potential plus the air pressure potential equals to metric potential plus change of pressure equals to 0. So in this case, metric potential equals to negative change of pressure. So at equilibrium, chamber is depressurized and the soil water content is measured. So at equilibrium, we will depressurize, means reduce the pressure back to atmospheric pressure, and then we will open the chamber, and then we'll take out the soil sample and measure the soil water content. That's why we know at a different pressure, what would be the soil moisture content in the soil. So of course, after we measure, we will close the chamber again and continue for the other soil at a greater negative pressure, and therefore we will know again at a different pressure what happened to the soil water content at different soil samples that left in the pressurized chamber. So this method may be used to achieve air gauge pressure up to 15 atm. So negative 1500 kPa is about 15 atm, 15 atmospheric pressure. Okay, waiting time for equilibrium is difficult to estimate, so it's very hard to know when is it achieve equilibrium. Okay, by using this method. Okay, just now I talked to you about the hanging water column and also the pressure plate. So the hanging water column can measure the pressure up to minus 10 kilopascal. Okay, and then the rest of the pressure up to negative 1500 kilopascal you can measure by using the pressure plate. Okay, so apart from hanging water column and pressure plate, so here's the range of pressure plate. There is also some other method, for example Hypro, Teros 21, there is MPS 6. Okay, there is also tensiometer. Tensiometer is quite accurate, and apart from that, and there is also WP4C. Okay, so if you look at here, from 0 up to negative 1500 kilopascal, it is best to cover by hanging water column as well as a pressure plate, and the rest of the column, the rest of the pressure, it is best to obtain it by using WP4C dew point. So with that, with these three instrumentation, basically we can cover the whole range of pressure that is needed. Okay, so here's a graph shows the characteristic curve. Okay, the characteristic curve shows the relationship between metric potential. Okay, metric potential. This one is in the scale of log, and with water content. Okay, water content. So it's a metric potential water content function. Okay, or in short we call it characteristic curve. Okay, so here is show the example for sand. Okay, so the characteristic curve for sand, and also the characteristic curve for clay. All right. We can basically divide all the characteristic curve into three regions: the air entry region, capillary region, and absorption region. Okay, for air entry region, metric potential changes, but the water content does not change. So you see that as the metric suction increase, the amount of water, the water content still remain relatively constant. So the minimum suction must be applied to saturate soil. The minimum suction must be applied to the saturated soil before air enter. So this is known as air entry suction. So the minimum suction must be applied before the water content started to drop. So when the water content started to drop, basically it means that the water started to drain from the soil. Okay, so 10 centimeter metric suction for coarse sand, to higher for finer sand. So if it's more finer, so it will be greater than 10 centimeter. The suction length. Okay, so if finer, so it takes a longer time before it starts to drain. Okay, for capillary region, so here is the capillary region. Drain big to small pores. Okay, drain from big pores to small pores happening here. So primary by curvature of the interfaces between air and water phases. Okay, so in this region you can see that small changes of metric suction, a large changes of a large drop in water content. So it means it requires a little bit of pressure to drain out a lot of water. Okay, so basically this region is also the region what we call the field capacity region. Okay, right. The absorption region drain from tightly bound water. Tightly bound water absorbed to particle surface. So you can look at this region. Okay, so you can see that a large changes of metric suction is required to cause a little bit drop in water content. So it means a large pressure is required to remove a small amount of water. Okay, so drain from tightly bound water absorbed to the particular surfaces. Large changes in metric potential, metric suction, but a small change in water content. Okay. Okay, so here is a hysteresis in water content and energy relationship. So in the previous graph, I show you only a single characteristic curve for sand and clay. But in reality, sand it can be sand can have two curves. One is for drying, and the other one is for wetting. Similarly, the same observation can also be reported for clay. You can have one for drying and the other one for wetting. So here is an example showing one typical soil that going through a drying loop and also the wetting loop. Okay, so why do we have different curve? So let us look at this the reason behind it. Okay, so doing wetting, okay, this wetting, okay, wetting, all right. During wetting, water enters small pore first. So the small pore of the soil will start take up the water first when it is first exposed to the water. Okay. Subsequently, the larger pore will be filled up. Okay. So small pore attract water, and then only the large pore will fill up with water. But during drying, okay, drying by evaporation and by outflow, drain start from large pore to small pores. Okay, so drying, so this is a drying curve. So it starts from draining from large pore to small pore. Okay, water held in the large pore will not drain until at least one of the interconnecting small pores can be empty. Okay, so this result at equal metric suction, the water content for wetting okay, is smaller than the drying. Okay, so drying has a larger water content than wetting. So at equal metric suction, because why? Because the water drain from large pore to small pore during drying process, but in the wetting, the small pore will be filled up first, then only by large pore. All right. So drying and wetting loop is known as a primary drying curve. So this is a primary drying curve, and also the primary wetting curve. So this is a primary wetting curve. Okay, and the interior of the hysteresis loop is known as scanning or secondary curve. So why is this happen? Why do we have this scanning or secondary curve? Because during the process of drying, up to this stage at this metric potential, suddenly, let's say we try to wet the soil. So at this stage, when we wet the soil will go through this process, and then suddenly we decided to dry the soil again. So when we dry the soil become this way. So and then we wet the soil again, saying go through this way. So this is the process as a result of drying, wetting, drying, and wetting again. Okay, so we can form this scanning or secondary curve, and you can see that it doesn't follow the primary or secondary of drying and wetting curve. Okay.